Hello students, in my today's video we'll discuss about the stereochemical aspects of nucleophilic substitution reaction. In my earlier video I have explained few terms like optical activity and racemization and had said you will explain in the next video. To understand it, first let us understand what do you mean by plain polarized light. So when an ordinary light is passed through a polarizer. So polarizer here is nickel prism. All the vibrations are adjusted and a light of single wavelength propagating in a single plane only are allowed to pass. This is called as plain polarized light. So let us understand it with a diagram. So we consider that you are having a source of light and this source of light is nothing but a bulb. So when you observe this source of light, how is the light emitted? Is the light emitted only in a single plane, that is only in one direction, or in all possible direction? We observe that it is emitted in all possible direction, and such a light we call it as an unpolarized light. So what do you mean by unpolarized light? The light moving in all possible directions, we call such a light as an unpolarized light. So what do we observe here? The light is not moving only in a single direction. The light is moving in all possible directions. So I hope I'm clear. So the light which moves in all possible direction, we call such light as an unpolarized light. So for we need what? We need a polarized light. So for that, what do? We take this unpolarized light, and the unpolarized light is made to pass through a polarizer, that is nickel prism. So we'll consider the unpolarized light. We will pass this unpolarized light through a nickel prism, and when it is passed through a nickel prism, that is the polarizer, the ray which comes out of the polarizer will be a single ray. That ray we call it as a plane of polarized light, or we can say polarized light, that is a monochromatic beam of light. And this monochromatic beam of light has light moving only in one possible direction. So the light moves in the form of, or travels in the form of what? Wave. So here we'll observe that only one possible wave is obtained, and such a plane we call it as what? Plane of polarized light. The difference between the two is, in the first one, in unpolarized, it was moving in all direction. In polarized, it is moving in one direction. So what is plain polarized light? When ordinary light is passed through a polarizer, all the vibrations are adjusted and light of single wavelength propagating in a single plane only are allowed to pass. This is called as plain polarized light. I hope this is clear. So once we know plain polarized light, we will go with the next concept, that is optical activity. So this was what I had said you. I'll explain it to you in my this video. So what do you mean by optical activity? So the rotation of the plane polarized light is called as optical activity, and here certain compounds rotate the light in clockwise direction or in anti-clockwise. Such compounds are said to be optically active. So to understand this, again we'll consider our example. So here what kind of light we had obtained? We had seen that when the unpolarized light was passed through a polarizer, the light which was coming out, we get it as a polarized light that is moving in a single plane. Now when this polarized light is made to pass through the solution, that is aqueous solution, that is of which compound? So we are studying about the organic compound. So we'll consider aqueous solution of organic compound is taken, and when this light is made to pass through the aqueous solution, we will observe two things: either the light will move in clockwise direction or the light will move in anti-clockwise direction. So what is that? So here one thing you have to keep in mind, that the organic molecules have the tendency to rotate the plane of polarized light either in clockwise direction, that is towards right, or in anti-clockwise direction, that is towards left. So we'll consider now will observe the plane polarized light. So this is what our light, plane polarized light. Why? Because it is moving in a single direction. So a polarimeter consists of an analyzer that through which you can observe the change in direction of the light. So let us consider here we are having a solution. Now this plane polarized light is made to pass to the solution. The molecules which are present in the solution, they can either rotate the plane polarized light in anti-clockwise direction or in clockwise direction, and based on this we classify them as dextrorotatory compound or levorotatory compound. So if it rotates in clockwise direction, we call them as what? Dextrorotatory compound. And dextrorotatory compound. And if it rotates in anti-clockwise direction, we call it as levorotatory compound. So remember, organic compounds are classified into two types, dextro and levorotatory compound. So let us consider why we say it as dextro. So we have a plane polarized light in a same direction. Through the analyzer, if you observe that there is a rotation in the light, that is in which direction? Anti-clockwise direction. So here you will see it was a straight line, that is a polarized light which was a straight line. Through the analyzer you will observe that it will move in right direction and the polarized light tilts slightly, and this direction, that is if it is rotating towards right direction, and if there is a change in the angle of the plane polarized light, that is it changes its plane, and towards which side it is moving, towards right side, and that we call it as dextrorotatory. Now consider levorotatory. For levorotatory we'll consider again, this was our plane polarized light, and through the analyzer if you observe that the plane moves towards which side? Left side. That is, you will observe the light moving towards left side or anti-clockwise direction, then we call such compounds as a levorotatory compound. So what is the whole thing we have observed now? In polarimeter, what do we see? The solution is placed, and through this solution, what is passed? We place an analyzer. We pass an a polarized light, and through the analyzer or detector we see the change in the rotation of the polarized light. If the polarized light moves towards left, or if the polarized light moves towards right, so we'll consider if it is moving in clockwise direction, it will show the tilt, that is a plane tilts towards the other side. We call it as what? Dextrorotatory compound. And if the molecules rotate the plane polarized light in anti-clockwise direction, that is towards left, which we observe through the detector, we call such compounds as levorotatory compounds. Thus, we can conclude that rotation of the plane polarized light can take place either in clockwise direction or anti-clockwise direction, and this rotation of plane polarized light itself is called as optical activity. Optical activity. The rotation of plane polarized light is called optical activity. Certain compounds rotate the plane polarized light either in clockwise direction or in anti-clockwise direction. Such compounds are said to be optically active. Next is dextrorotatory. So the optical isomers which rotate the plane of polarized light towards right or in clockwise direction is known as dextrorotatory isomer. These are indicated by plus sign or D before the name of the compound. Next is levorotatory. The optical isomers which rotate the plane of polarized light towards left or in anticlockwise direction is known as levorotatory. These are indicated by a negative sign or L before the name of the compound. Optical isomers, compound having same molecular formula but differ in the spatial arrangement of the atom and thus differ in the direction of the rotation of plane polarized light, are called optical isomers, and the phenomenon is called as optical isomerism. Consider the example of optical isomers. So what we have discussed in the definition, molecular formula should be same. So let us see the formula: carbon and carbon, then HOH, other side also OH and H we are having, then CH3, CH3, and COOH, COOH. So what do we observe here? Molecular formula is same. What was the second condition? Arrangement of the atoms was different. So we'll see here what is the arrangement of the atom in the above example. So OH here, it is present on which side? It is present on right side. Whereas in the other example, OH is present on to the left side. Because of which, what do we observe here? We observe that the arrangement of the atoms is different, and hence, since the arrangement is different, rotation of the plane polarized light will also be different. So what do we say? Rotation of plane polarized light is different. Why it is different? Due to the position of the OH group. That is, the OH group is present on to the right side. So we'll assume that it is dextrorotatory with positive sign. Hence the other will be levorotatory. So OH group is present on right side here and on the over there left side. So what was the definition? Molecular formula is the same, arrangement of atoms is different, and the rotation of the plane polarized light is different. That is, the rotation can be either in which direction? That is right direction or towards left. So such isomers we call it as optical isomers, and the phenomenon is called as optical isomerism. What is chiral carbon atom or asymmetric carbon atom? The carbon atom which is connected to four different groups or groups of atom is called as chiral carbon or asymmetric carbon atom. So let us consider an example. So one carbon which is surrounded by CH3, then on another side by COOH, then on another side by H, and on another side by OH. So here we observe OH, H, CH3, COOH are completely four different groups. So what do we observe? Carbon is surrounded by four different groups. Such a carbon we call it as chiral carbon atom, or we call it as an asymmetric carbon atom, or we call such a carbon as a stereogenic carbon, or that carbon is called as stereocenter. So let us consider a molecule. So that the ball which is black color is carbon. So we'll consider 1, 2, 3 and 4. 4 different atoms are present around the carbon atom. So that carbon we call it as a chiral carbon atom or asymmetric carbon atom, or we call it as a stereocenter. Before understanding what are enantiomers, let us understand what do you mean by superimposable and non-superimposable images. So to understand it, consider the example. So in superimposable and non-superimposable, to understand it, we'll consider one example. So take a molecule. Now when you place a mirror beside in front of it, exactly you will observe it's a mirror image. So here you will see that the one which you have placed onto the left side is exactly equal to that of the one which is present onto the right side. So that becomes our mirror image. Now when you place the mirror, you have observed it. If you take that the image which is obtained here, now if you take that mirror image, so equal position of the atoms we observe here in the mirror image. Now consider that one of the image, that is mirror image, you take it and place it above the atom. So when you place that mirror image above the atom, what do we observe here? So you can see that the position of the molecules do not coincide with each other. If they coincide with each other, we call it as superimposable. But the one which is present at the top are only occupying the same position and carbon atom. What about the other atoms? They are exactly present opposite to each other. So they are not coinciding with each other. They are not in a same line. So let us take another example. Think that you place your hand, you place a mirror beside your hand. You will observe the mirror image of your other hand. Now when you take that mirror image and place it above the other hand, Are all the fingers coinciding with each other? Is the thumb of your finger coinciding? Is the thumb finger coinciding with the thumb of the next hand? No, they are not coinciding with each other. So what do we say? These are not superimposable. So the one which coincide with each other, we call them as what? Superimposable. Let us take another example to understand this concept. So take a ball. Now when you take a ball and place it, and in front of that you place a mirror, and after you place a mirror, you will observe its mirror image. Now what is a mirror image you are getting? Here also you were having a ball, here also you were having a ball. So are the both matching with each other? Is it coinciding with each other? Yes, we observe that it is coinciding with each other. So such images we call it as what? Superimposable mirror images. The one which coincide are superimposable mirror images. Let us take another example to understand this concept. So we'll consider an example of a molecule which is surrounded by two atoms. So we'll take this example. We will place it, and beside it we will place a mirror. Then we'll observe the mirror image. So red atom should appear beside the mirror, then the black, and then the blue ball. So what we observe here? So this is exactly, or you can say this becomes your exact mirror image. So what do we observe? See, you can see when you place the mirror in between, exactly what kind of image you are getting. We'll take that mirror image and we'll place above the other image. So what do we observe here? The atoms have changed their position. They are not coinciding with each other. If the red would coincide with the red, and if the blue would coincide with the blue, it would be a superimposable. But since they are not coinciding with each other, it becomes a non-superimposable mirror image. So such images we call it as what? Non-superimposable. As discussed earlier, so the images which coincide with each other are called as superimposable. So consider the below example. CH4, you place a mirror, so you will get exactly the same structure. Now when you place that structure above it, you will see that the carbon, hydrogen coincide each other, carbon coincide, in every atom of it coincide with each other. So all the hydrogen are equivalent, so they will coincide with each other, and hence we call such images as which images? Superimposable images. Then next, let us consider the images which do not coincide with each other. We call such images as non-superimposable mirror images. Take an example: carbon surrounded by hydrogen, OH, CH3, COH. So what do we observe now? If you place a mirror, what will you observe? CH3 to the other side. On placing a mirror, first you observe CH3, then the hydrogen, then COH, then carbon, then OH. Now when you take this mirror image and place it above the other image, that is on the left side, so what will happen here? C will coincide. C and C will coincide. H and H will coincide. COH will coincide. But what about CH3 and OH? CH3 goes in the place of OH, and OH in the place of CH3. So what do we observe here? Change in the position of CH3 and OH. So what do we say? This do not coincide with each other. Hence it is a non-superimposable mirror image. The next is enantiomers. So what are enantiomers? A pair of optically active compounds which are non-superimposable mirror images of one another are called enantiomers. They have identical physical properties like melting point, boiling point, refractive index, etc. And they only refer with respect to the rotation of the plane polarized light. So let us recall the example here. This was the example for optical isomers. So here they are having same molecular formula. So if one is this is an example of lactic acid. So if one is levorotatory, another will be dextrorotatory. One is the mirror image of the another. Don't get confused. It is just a comparison between the two different molecule. So what do we observe here? When you place the mirror image of the other onto the first atom, are they superimposable with each other? They are not superimposable. Why? Because the position of the H and OH are different. So such images which are not superimposable, we call them as what? Non-superimposable mirror images, and the isomers which have same molecular formula and have non-superimposable mirror images and are optically active, that is one will be dextro, another will be levorotatory, such isomers we call them as enantiomer, that is a pair of isomer which have non-superimposable mirror image and are optically active, we call them as what? Enantiomers. So consider the examples here. So one of them will be levorotatory and the other is dextrorotatory, and this pair of isomers which are optically active we call them as what? Enantiomers. Next, let us consider chiral and a chiral molecule. The molecules which are non-superimposable on their mirror image are said to be a chiral molecule, or the molecules which do not contain a plane of symmetry are said to be a chiral molecule. Consider an example. So when you consider carbon bonded to four different atoms, we call such carbon as chiral carbon. We take the mirror image, and on taking the mirror image, whatever the mirror image we are getting, we place it above it and we find that it is not superimposable. So we say that it is chiral. And when you take the compound, let us write the same compound, that is carbon surrounded by four different groups, and if you divide this compound in such a way that you get two equal parts and the atoms, similar atoms on both the side. Do we get similar atoms on both the side? We cut in any plane, we don't get similar atoms on both the side. Thus we say that it does not contain a plane of symmetry. Such molecules we call them as chiral. Let's go to achiral. So achiral means what? Opposite to that of chiral. So the molecules which are superimposable on their mirror images are called as achiral molecule, or the molecules containing a plane of symmetry are called as achiral molecule. So let us take the example of benzene ring. So if you divide benzene ring into two parts, you get equal atoms on both the side. You divide it in any way, you get equal atoms on both the sides. So let us consider other way of cutting the benzene ring. It also gives equal atoms, so it is achiral. What is a racemic mixture? So racemic mixture, which I had discussed earlier, we get this as a product in SN1 reaction. We'll understand it. A equimolar mixture of D and L isomer of the same compound is called as racemic mixture. What does it actually means here? Now we'll consider that we are having a solution which contains 50% of dextrorotatory isomer and 50% of a levorotatory isomer, and this mixture we call it as what? Racemic mixture. So what happens actually in this mixture? So when the plane polarized light, so we'll take the plane polarized light which moves only in one plane, is passed through a solution which contains what? 50% dextrorotatory compound which can rotate the plane polarized light in clockwise direction, and which contains a levorotatory compound which can rotate the plane polarized light in anti-clockwise direction. So when the plane polarized light is passed through such a solution which consists of half of them dextrorotatory and half of them levorotatory molecule, so half will move in clockwise, half will move in anti-clockwise, and through the analyzer we will observe that there is no change in the polarized light. Why? Because due to equal clockwise rotation and equal anti-clockwise rotation, there will be no change in the polarization plane. The light will be moving in same plane, and we call it as what? Zero optical activity. So we'll recall the definition of racemic mixture now. So do you mean by racemic mixture? A equimolar mixture of D and L isomer of the same compound which is optically inactive or have zero optical rotation is called as racemic mixture. So why it is optically inactive? It is very important for your exam. So you should remember that because of the presence of D and L isomer. The term equimolar mixture and optically inactive are to be mentioned in the definition if it is asked for 1 mark. And the process of conversion of enantiomer into a racemic mixture is known as racemization. Don't get confused with enantiomer and Racemic mixture. Enantiomer is nothing but comparison between two different isomers which differ only in the position of the nucleophile. Molecular formula is the same, but the position of the atoms is different. Whereas racemic mixture means what? It is a mixture. It contains both the isomer, that is 50% of D isomer and 50% of L isomer. So don't. Then next is retention of configuration. So during a reaction, if the reactant has the same configuration of groups around the chiral or stereogenic carbon atom as that of the product, then we call it as what? Retention of configuration. So let us understand it with an example. So consider an example, that is carbon atom which is bonded to four different groups. Why we'll consider four different groups? Because it is a chiral carbon atom. So A, B, C and X. So we'll consider X as our nucleophile which has to be exchanged. So we'll consider the reaction with another nucleophile. So if the nucleophilic substitution takes place in such a way that another nucleophile occupies the same position of the nucleophile as that of the reactant. So if Y goes in the place of X, and the product obtained will be what? Now here we are having carbon atom which is bonded to A, B and C, and instead of X what we have seen? Substitution of nucleophile Y. So on both the side you will see that the removed atom was present on which side, which was nucleophilic in nature, on the right side, and the one which has attached to the carbon atom also gets attached to which side? Right side. Since the nucleophile are present onto the same side, we call this type of configuration as retention of configuration. So this is what we have discussed. I had said I'll discuss it in my this video. Version of configuration. So during a reaction, if the product formed has opposite relative configuration as that of the reactant, then it is called as inversion of configuration. So what do you mean by inversion of configuration? We'll see. We'll take a carbon atom surrounded by four different groups. So we'll represent it as A, B, C and X. So this X is a nucleophile that has to be substituted, that is nucleophilic in nature. So it will be substituted by another nucleophile. Let us consider our another nucleophile. Now if this nucleophile attacks from the rear side, that is from the back side, so what kind of product we obtain? We get the nucleophile exactly in the opposite direction to that of the nucleophile which was present in our reactant. So we observe that Y, then it was bonded to B and C. So here we observe that X is present on which side of the reactant? It is present on the right side of the reactant, whereas in the product the nucleophile is present on which side? Left side of the reactant. Thus the definition says that if there is the product formed has opposite relative configuration as of the reactant, we call it as what? Inversion of configuration. So let us recall, in my previous video I had said that the kind of product obtained in SN2 reaction has inversion of configuration. So we'll recall the reaction quickly. So nucleophile will attack methyl chloride. So the nucleophile in SN2 attacks from which side? From back side, that is rear side. When it attacks the leaving group is Cl. So OH will occupy the position exactly opposite to that of the Cl. So we get OH, that is alcohol is formed. Then HH and Cl. So what do we observe here? Cl is present on which side of the reactant side? It is present on to the right side. Whereas OH is present on which side? OH is present on to the left side of the product. So we observe the change in configuration. It is called as inversion. Discuss in detail inversion, retention and racemization. So let us consider an example. So when you take the example, so this is an example which is given in your NCERT textbook. So a carbon bonded to C2H5, X nucleophile on one side it is bonded to methyl group, and on another side it is bonded to hydrogen atom. So here we will study the nucleophilic substitution reaction. So let us consider that this reactant, when it is made to react with the nucleophile Y. So here you will observe the nucleophile Y will see the attack from two sides. One is from the front and one is from the back side. So when you observe the attack from the front side, just what happens, the position of the nucleophile will be exchanged. That means what, in the position of X we get Y. So we'll write its structure. So we'll obtain the structure as Y, then methyl group, and we are having an hydrogen atom attached to it. So the nucleophile has been placed on the same side of the position. So what do we observe here? Since the nucleophile is present on the same side, this process we call it as what? Retention of configuration. So this is what we have observed in previous example. Next is when the nucleophile attacks from back side. So when the nucleophile attacks from back side, we see that a open umbrella like a structure is formed, and the nucleophile will acquire the position opposite to that of the reactant. That is, in the reactant, if your nucleophile is present onto the left side, in the product the nucleophile will be present onto the right side. So that itself we call it as what? Inversion of configuration. So this is what we have already studied: retention of configuration and inversion of configuration. And what do you mean by racemic mixture then? So let us consider the retention of configuration as A and B, inversion as B. So if you are having 50% of A along with the 50% of B, then we call it as what? Racemic mixture. That means if you are having a mixture, half of which it is dextrorotatory and half levorotatory, we call it as what? Racemic mixture. So we'll recall what we had studied. So in SN1 reaction, in step 2, we have studied that the nucleophile attacks the carbocation. So this was our carbocation in the step 2. The nucleophile can attack either from the back side, or the nucleophile can attack either from the front side. So what are the two possible products we get here? It is not either, sorry, it will attack from both the side, and we get a mixture of a product. That is, one will be present onto the left side of the nucleophile will be present on the left side, and another nucleophile will be present onto the right side. So here one will be dextrorotatory, another will be levorotatory. So we get a mixture of 50% D isomer and 50% L isomer, and this we call it as what? Racemic mixture, and the process is called as racemization. So let us recall the concepts discussed in today's class. What are enantiomers? Give example. Then what is an chiral carbon, asymmetric carbon or stereogenic carbon? What is a racemic mixture? What are dextro and levorotatory compounds? What do you mean by optical isomerism or define optical isomerism? And optical activity of product in SN1 reaction and SN2 reaction. So these are the important questions from this part. I hope you like this video. Thank you for watching. Please like, share and subscribe.